Hey, this is Charlie Thompson. Welcome to Atmospheric Water and Weather. This is going to be, I think, just the first couple modules. Module 1 and Module 2 seems like that would make a nice bite-sized chunk, but let's see what happens. So there's a picture of a big scary cloud and a little tiny photographer off in the lower left there taking a picture. Yeah, whatever. There you go. How does water behave in the atmosphere? What are the forces that produce our weather? The answer to that question is the latent heat of condensation. That is the most important idea of the entire chapter. The whole key to understanding why we have weather, why we have rain, especially things like tornadoes and thunderstorms and hurricanes, all of those are the result of the latent heat of condensation. When water vapor condenses, it releases heat to the atmosphere around it. So it actually warms stuff up. When water vapor condenses, it warms stuff up around it. What causes violent storms? The answer to that is the latent heat of condensation. So, yeah, everything you need to know about the latent heat of condensation. Water is the weirdest substance on Earth. If there was a substance on Earth that I was going to try to pick that didn't come from Earth because it doesn't behave like anything on Earth, it'd have to be water. Water has some of the highest specific heat of any compounds, of any substances on the planet. It takes more energy to change the temperature of water than just about everything else. Water dissolves more things than anything else. I think it dissolves 57 or 58 of the known elements. So it's the most corrosive substance on the planet. It's the only substance that appears as a solid and a liquid and a gas at normal Earth temperatures. Everything else is pretty much usually just one state, like it's either a solid or a liquid or a gas. But water is the only one that's a solid or a liquid or a gas at normal Earth temperatures. And water is also the only substance that expands when it freezes. And I'll talk more about that. So this is review. A calorie is the amount of energy that it takes to change the temperature of a gram of water by 1 degree. Phase change refers to water changing from one state to another, from solid to liquid, liquid to gas. And latent heat is the energy absorbed or released during phase changes. So I know it's really weird. When ice melts, it goes from being solid ice at 0 degrees to liquid water at 0 degrees. The temperature doesn't change, but it went from being a solid and now it's a liquid. So here are the 3 states of water. Water is, let's see if I can grab the pointer. Water exists as a vapor. Water vapor is a gas, just like oxygen and nitrogen into the atmosphere. The fact that it condenses is different than oxygen and nitrogen, at least at the normal Earth temperature. So gas appears as water appears as a vapor. Liquid water, we all know liquid water. The molecules are actually farther apart when water is liquid than when water becomes solid. Solid ice, the molecules lock together. You can see there's a picture here of the hexagonal shape. The hexagonal shape, when the molecules get locked together, it expands 9%. So water is the only substance that expands. If water acted like everything else, ice cubes would be at the bottom of your drink, icebergs would be at the bottom of the ocean. And I also have to talk about this, that the actual shape of water. Water looks like Mickey Mouse. It's got 2 hydrogen atoms, 1 oxygen. The hydrogen is positively charged, the oxygen is negatively charged, so they stick together. This allows for things like capillary action when water spreads throughout a towel or an absorbent substance. That wouldn't happen if the molecules didn't stick together. So without the hydrogen bonding and without this shape, not only would water not act wet, but ice would expand when it freezes just like everything else, and life on Earth would be completely different if water didn't act unlike everything else on Earth. Some of the calories involved, I'm going to grab the pointer again. To melt a gram of ice takes 80 calories, and then you have water at 0 degrees. So the temperature is the same. You've got ice at 0, water at 0. The temperature is the same. It's just absorbed 80 calories of heat, and now it is a liquid. If we keep adding energy, we add another 100 calories, we're going to change the temperature of liquid water to 0 to liquid water at 100 degrees. And then as we keep adding heat, after we've added 540 calories, the water at 100 degrees will become water vapor at 100 degrees. So again, the temperature didn't change, but the state changed. It went from being liquid drops of water to a gas, just like oxygen, just like nitrogen. And when that water vapor condenses, it's going to release 540 calories to the air around it, warming the atmosphere. Just like when ice, you have to pull the 80 calories of energy, of heat energy out of water to make it freeze. The temperature is the same, but now it's a solid instead of being a liquid. So that's the latent heat of freezing, and melting is 80 calories. To melt it, the heat has to be absorbed. To warm it, the heat is absorbed. To make it evaporate, 540 calories have to be absorbed. When water vapor condenses, it's going to release 540 calories. As water cools, it's going to release 100 calories. And then finally, when that water freezes, it's going to release another 80 calories. So every time it goes from water vapor to water, heat is released. When it goes from liquid to solid, heat is released. Humidity is just talking about water vapor in the air. Again, it's a gas, just like oxygen, just like nitrogen. The amount of water vapor you can have is a function of the temperature. The higher the temperature, the more heat there is. The more heat there is, the more energy there is to evaporate water and keep it evaporated. The higher the temperature is, the more energy is available to evaporate water. The first type of humidity I'm going to talk about is specific humidity. It's one of the ways that scientists measure or let you know how much water vapor is present, and that's specific humidity, where they're telling us the mass of water vapor per kilogram of air. So it's just telling us how much we have. Mass of water expressed in grams per kilogram of air. A kilogram of air has a volume of about a cubic meter, so about 3 feet by 3 feet by 3 feet. That blob of air weighs about 2.2 pounds, which is a kilogram. Relative humidity is different than specific humidity. Relative humidity is the amount of water vapor you have compared to the amount of water vapor you could have. This is a chart of maximum specific humidity. So at any one temperature, there's only so much energy that can evaporate only so much water. So at 0 degrees, there's enough heat to evaporate 4 grams of water. At 10 degrees, it's about 8. At 20, it's about 15. At 30, it's about 27. And at 40, it's about 47 grams. So you can see every time the temperature warms by 10 degrees, the maximum specific humidity just about doubles. 4 grams, 8 grams, 15, 27. You can see as temperatures increase, it kind of breaks down. It's not as accurate. But negative 20, you've got 2 grams. Negative 20, you've got 1 gram, 2 grams, 4 grams, 8 grams, 15. So every time the temperature increases by 10 degrees, the amount of water vapor you could have just about doubles. It doesn't mean you have that water vapor. It just means that there's enough energy to evaporate twice as much water vapor. Relative humidity is the amount of water vapor that is present divided by the amount of water vapor that you could have at that temperature. The amount present is how much you have. Usually, and for most of the problems that we're going to do, that's going to be grams of water vapor per kilogram of air, which is going to be specific humidity divided by the amount possible. That's going to be the maximum specific humidity. That's just a function of temperature. When the relative humidity is 100%, we say the air is saturated. If you add water or cool the air, you're going to get condensation. So here is an example. If it's 5 o'clock in the morning, let's say the temperature is such that we have 4 grams of water vapor. The maximum is 4. We have 4, so the relative humidity is 100%. A couple hours later, if it warms up remember, every time it warms by 10 degrees, the capacity doubles. It doesn't mean the amount of water vapor doubles, but the capacity doubles. So now it's gotten warmer by 10 degrees. Our capacity is 8 grams. We only have 4, so our relative humidity is how much we have, 4 divided by the max, 8, so it's 50%. If the temperature gets warmer by another 10 degrees, the maximum is going to double again, so now the maximum is 16. The amount present, still only 4, so the relative humidity drops again to 25%. So let me go back to this chart, if I can find the chart. Let me go back to the chart, and there's the chart. So on the chart, you can see as the temperature increases, the capacity doubles. So if the water vapor stays the same, for example, on that first slide, or the first part of the diagram, it was 0 degrees with 4 grams, so that's 100%. As the temperature increases, the capacity increases. So now you could have 8. If you still have 4, the relative humidity has now been cut in half, because the maximum doubles every time the temperature gets warmer by 10 degrees, but it doesn't mean that you actually have that extra water vapor to keep it at 100%. It just means that the relative humidity is going to go down. As the temperature goes up, if the amount of water vapor stays the same, the relative humidity goes down. As the temperature goes down, then the relative humidity is going to go up. So that same problem again. So if we go back here, it's 20 degrees, the maximum is 16, we have 4, so the relative humidity is 25%. If the temperature cools off by 10 degrees, the capacity gets cut in half. So we still have 4 grams, but now the maximum is 8, so the relative humidity has doubled. As the capacity goes down, the relative humidity goes up. Same thing is going to happen again. As the temperature decreases, the relative humidity goes from 50% now to 100%. The capacity is 4 grams. The amount we have is 4 grams. 4 over 4 is 100%. Here's a temperature trace from the Sacramento airport. And you can see when the temperature, here's the highest temperature during the day, lowest during the day, highest during the next day, lowest. That the highest temperature has the lowest relative humidity. And the part of the day with the lowest temperature has the highest relative humidity. So they're an inverse relationship. As it gets warmer, unless there's more water vapor, the relative humidity, as it gets warmer, the relative humidity is going to go down. As it gets colder, the relative humidity is going to go up. Dew point temperature is the temperature at which a given mass of air hits 100% relative humidity. So in that last example, this air is at dew point temperature. The relative humidity is 100%. If we make it any colder, we're going to get condensation. If we try to add water vapor, we're going to get condensation because it's actually at dew point temperature. If it's below 0, then we call it frost point and frost accumulates, but we live in Sacramento, so we don't get a lot of frost. Here we have a diagram showing the average total precipitable water. So this is specific humidity. It's expressed slightly differently, but it's still more or less just telling us how much water vapor is present. Here along the equator, this is actually the ITCZ. Right in here, this belt of high moisture air, that's the ITCZ. The air there is rising, it expands, it cools, you lose moisture, so the air gets drier, and then when it sinks, it heats up, which further makes it drier. So right here, subtropical high, subtropical high, subtropical high, subtropical high, subtropical high. There's sinking air, the air gets warmer, so the relative humidity and the specific humidity is much, much drier here. And then as you go farther north, it's drier now because it's just cold. The colder it is, the less energy there is to keep water vapor. So again, the pattern, it's all latitude, right? The lowest values are at high latitude and the highest values are at low latitude right here in the ITCZ. And you can really, again, see the difference between the ITCZ. Here's the Amazon, Central African rainforest, as opposed to the Sahara, or the Atacama Desert, or the Namib Desert, or the Skeleton Coast of Namibia, the Kalahari Desert, the American Southwest, Saudi Arabia, all of those places. Australia, much of Australia is desert. This is a sling psychrometer. It has two bulbs. One of them is wet. That's called the wet bulb. The other one is dry. That's called the dry bulb. So you get the wet bulb wet, and then you spin it around, and as you spin it around, water evaporates. As water evaporates, it absorbs heat from the thermometer. So the more water evaporates, the lower the wet bulb temperature gets. So the drier it is, the more water evaporates, the bigger the difference between the two thermometers. So if there's a really big difference, it means that there was a lot of evaporation. That means that the relative humidity was very low. There was still lots of energy available to evaporate water. If they are the same temperature, that means that there was no cooling. The reason there was no cooling is because there was no evaporation. The reason there was no evaporation is because there wasn't any energy to evaporate water. So the relative humidity would be very, very high. In fact, if the relative humidity was 100%, there'd be no difference between the temperature of the wet bulb and the dry bulb thermometer. We're up to atmospheric stability, so I'm just going to pause this for now. And the next one is the next video is going to be all about atmospheric stability.